A comment for you.
What's up?
Then I started doing the presentation. I'm like,
Yeah. So I didn't take any like screenshots at the meeting. So I was like, okay, I'm just gonna do this in my apartment.
I forgot the password.
Huh?
I forgot the new password.
I didn't. So but as like I go on my laptop, I get onto the server and I type in the Gauss view, and it just says cannot connect to server. I'm like, what? Why can't I connect?
Did you guys go over how to connect to like
Yeah.
on a local laptop?
Oh, you can't.
Yeah, I mean, as long as you have like
I have
some
like
kind of
portable.
terminal.
It's those. You have to be on the supercomputer to get Gauss.
But it kept saying,
Oh,
Can you
man.
pass this around?
Are these 3 of them for me? What? I'm confused.
Depending on your performance. One for everyone, and then Steve around afterwards. Okay, well, thank you for investing your time into this activity. This is CHEM476 course, right? Slash 676. Right. Thanks for coming. Today's meeting number 8, and we are finishing the first chapter in the course. So the overall philosophy of the course that is not new for you. We are getting theoretical background. We are learning how to build molecular models, and then it is running on the right hardware with right software. And then observables are compared to experiments. Whenever possible, we try to follow this procedure. Focus. So when speakers will come here, they will be seen. So we are at the lecture number 8, and we are finishing the subject of molecular modeling. There will be 3 more chapters: electronic structure with Hartree focus, functional theory, and excited states. The lectures are accompanied with labs where we practice practical skills, which is probably most interesting. And today there will be special session when the material is taught by students, by attendees of the class, by young talents. And the goal of today's meeting, the goal of this arrangement, is that the practical skills that we get in the web sometimes are hard to focus on for the whole period of time. And we have elected and selected experts in each specific area, where this expert will present his or her story of success and failure, and help others to follow the success and avoid failures. So the main goal is to get practical skills in preparing atomistic models for our future investigation with electronic structure, using all facilities of supercomputing and special drawing software. Approximately, we plan on 3 minutes presentation and 3 minutes for slowly coming up, slowly coming back, and everyone is invited to ask questions and for questions. So if we follow this approximate schedule, we will be done in 1 hour. If not, so if you speak longer, it means you hold your classmates longer. In your printouts, there are more detailed list of subjects that are covered. And if you are seeing Microsoft Windows computer for the first time, we check it out. Here is the protocol, what you do when it is your time to present. So you come to the desktop, see your number and your name, click twice, and then click on this little square symbol. When you're done, you either close the presentation or send it to the background to give stage to other presenter. With this, I would like to call to the stage Alicia Roberts to tell us something about Linux and clusters.
Yeah.
The floor is yours.
Do I have to click on here every time I want to change it, or is?
Well, I mean, you have the
You can just
arrow
click on
keys.
like the, yeah, the
Ooh.
arrows. Oh, sorry.
I haven't thought about the
Oh,
clicker.
fancy. Alright. Alright, so what I'm going to be talking about today is distributed computing, basic Linux commands, file transferring, and job submission. So start with distributed computing is basically using a remote computer to work with your local computer to achieve a common goal. So generally, well, in our case, it's using our local computers to send a job to a supercomputer so that the supercomputer can do the computing and we can look at it on our computer so that it's not, all doing it on our one local computer. One of the benefits of it is there's no need to be near geographically, so you can do this from anywhere, so that there's no need to be connected directly to the computer. And it's more cost efficient just because multiple people can be using the same cluster. And so when all these computers work together, the whole system can be considered a cluster. So basically the computer that you're working on and also the computer that it's going to and any other computers that are working with that computer are all considered the cluster. But the main thing that's being worked on is, this having the worked on is the computer. Alright, and then this is just a basic picture of what it would look like. Is multiple people can be working with the server and they each send a request and then get a response back so that they don't have to process it on their own computer, which would be a lot slower. Okay, so basically how to log into Cluster. You have to open a terminal, whether that's Putty or Sigwin or whatever you want to use. And then in this, you use general Linux commands. I saw something about Unix. I don't know enough to know the difference. So I'm just going to say Linux commands, even if that's not 100% correct. I don't know what's on that. Oh, is that why? Okay, got it. Okay. Sorry. Okay, so you use the remote X connection, which will be talked about in the next presentation, so I'm not going to go too much into it. But basically, it's just a command to log into another computer. So it's like called a secure shell. I'm assuming the H comes from shell, but I'm not 100% sure. Anyways, so this would be the username, which is conveniently blocked out. And so you just use this command, and then this connects you to the cluster being accessed. So these two, the block obviously is going to stay the same, and then the hpc.usc.edu is also going to stay the same. Okay, so basic Linux commands are pretty simple. They stay the same mostly for most computers. Some of them can be you can vary them if you want to, but a lot of them are generally the same. So the first thing is make a directory, which is where you'd probably be working in. So there can be other files in this directory, and there can be other directories inside of the directory. Yeah, that's basically it. And then list files and directories that are in that directory. So it'll show, if you press ls, it'll show everything that's in that directory. So it can be files or other directories. And then cd changes directories, so you can go up or down the chain of command, whatever you want to say. Ooh, I'm me. So if you use that it will bring you back to the directory that you were just previously in, or so the higher up, or like the overarching directory, like below that or above it, whatever you want to consider it to be. And then pwd is really useful if you are trying to transfer files someplace, because it gives you the entire name chain of where you are. So all the directories before that, also the directory that you're working in, and possibly the file, depends on what you want, so that you can copy that later. And then nano is used to edit it, and then afterwards you have to have the file name and the type of file, so .com or .log or whatever kind that you're using. And then more just shows what's inside of the file. Okay, so SFTP is a secure file transfer program, and this is used for, this is downloading files, but you can't see it, but that's what it says. So you can use it for downloading and uploading files. So if you want to copy a file from the remote computer to your local system, that is downloading a file. And then uploading it is the reverse, but I'll make sure that's very clear. Okay, so if you're going to download it, you use a command that has the SFTP in the beginning, and then it's a space, then the username that you're under, the cluster, and then the target directory with the file name, and then the space and the period at the end are very important, as he so kindly added. I did not have that in there, but yeah, so that's the basic command that you would use. And then for uploading files, it's uploading files from your local computer to the cluster, so it's the opposite of downloading, which would make sense, but okay. And then it's the same type of thing, but it's a different order of operation. So you use the SFTP in the beginning again, and then the file name, then again your username, the cluster name, and then the target directory. And then, okay, just to make it very clear, uploading is from a local computer to a remote computer, and downloading it is from a remote computer to a local computer. It's just terminology, I don't know. And then job submission is, you have to open Gauss view if you're going to work with Gauss view or whatever you're going to work with. But specifically, I'm just going to talk about Gauss view. And then you have to save the file name in the .com format. I think that's going to be gone over in a different presentation, but I'm not 100% sure. But basically, when you save it, you just make sure it's under .com and send anything else. And then you use this command to run Gaussian, and then file name .com, and then negative or like -s, and then 4. I don't know what that last part means, but the normal part you can pretty much guess what it means. And then it submits the job to the remote computer for them to compute, and then send the results back to you. And then if you want to check whether or not it's running or not, you hit qstat, and then you can see whether or not your file is in the queue, or if it is running, or if it was terminated. Well, if it isn't there, then you know that something went wrong. And then if you put tail file name, it'll give you the last 10 lines of your file, and we'll show you whether or not it if it computed normally. It'll say job terminated normally, and that's if you do the file name and then the dot out. I think that's it.
Okay, let's thank Alicia. Anyone wanted to learn something from her? Jabbat?
In SFTP, you said that period is important. What is the importance and what does it mean?
I did not add that, so I'm not sure. But I'm assuming that it just means that it ends where the file, the end of the directory path. But I'm not 100% sure.
Satisfied?
I mean, I don't know.
Alyssa, on your third slide, if you can maybe go back to it quickly, on your presentation, you showed a Y file, and then on here we have an X file.
Yeah,
I guess I've just always been confused so far, while we're learning this, and if you don't know it, that's fine. What's the difference between the two?
I don't know the difference, but yesterday in lab we used Y, and for the X connection, in previous times we used X. I'm not 100% sure, but hopefully the person who has the X one will go over it. So, I don't know.
More questions? If there are no more questions, we'll thank Alyssa once again. And Russell Hoffman is invited to the stage. So I'm updating you on the timing. So we are already 3 minutes behind the schedule. So can you bring your presentation up? So let me know if you need to leave literally at noon. If not, we can go a little over.
I accidentally created a slide.
You know F5 works, right?
Okay, so I'm going to be first going over how to connect to the SeeCast, which is the university's HPC, and then how to set up X connections, and then use a visual connection through the HPC. the blank slide. Okay, so creating a SeeCast account, you'll need to go to the SeeCast website, which is seedcast.ndesu.edu, and it'll have on the left-hand side an apply hyperlink, which will take you to something like this here, and you'll have to input all of your information, change your title to whatever your status is at the university. You will need a faculty advisor, which can be any professor at the university, provided they agree to be your sponsor, which it doesn't cost anything to use the services. It's more so if you do something bad, then they can blame that person. Once you've done that, you'll also need to enter, or you should enter the software you want to use down here. So for this, you want to use Gaussian. One thing though, Gaussian has a separate user agreement from Gaussian, who says, or who doesn't want you to do bad things with their software. So you have to email support and tell them you want to be added to the Gaussian app group, and then they'll send you a user agreement you need to sign and send back to you. And please read the SeeCast user policies. I just I just read through it to look for mistakes the other week. I don't know if any changes have been made, but it should be better. So submitting Gaussian job to the USD. For this, you will need your input file, which will be some file dotcom, which you can create with the Gaussian app, or if you've done it a few times, you can probably just write it yourself. So when we run jobs on the USD, we use a script. We use the run Gaussian script. So run Gaussian followed by the file name, or the file name -s, which denotes the amount of scratch space, and then you'll need a number. And I believe it interprets your number as gigabytes. By default, the script will use one processor and 1 gigabyte of memory, but it allows you to use up to 24 processors and 95 gigabytes of memory. And you can modify those values by adding a header to your input file using %mproc shared followed by a number, and %memory equals a number followed by GB. And then after you add that header, just add a blank line. And it will use those numbers to supersede what's written in the run Gaussian script. I think Dr. Killen wants us to use the default. Okay, so if you're on the SeeCast, which uses a different program to do the queuing, it uses Torque. So you'll need 2 files to run a job on the SeeCast. You'll need your input file again, and you also need a PBS script, which I'll have an example on here that for the most part you can just copy it exactly to submit your job. Both need to be in the same directory, and to submit the job, you actually submit the script using qsub followed by your script, like a PBS script name. I'm not going to go through this. This is an example of a PBS script, which I have some notes added on here, but it would take a long time. We haven't gone through it. But we'll send this out so you can look at it. And I believe this is also added to the SeeCast website. So if you're trying to submit a job on SeeCast, you use qsub file name PBS. And then if you want to check a job, and this works for whatever HPC you're on that has a queuing system, use qstat-u followed by your login name, and it should give you a list of the jobs submitted by that user. So it'll have job ID, your username, queue it's in, job name, and then if you want to kill the job, you use qdel followed by the job ID. For SeeCast, it uses a number system. It may be slightly different on other systems. Okay, so the X window system. So X window system is what Linux uses to transfer visual information. It's in a bitmap format, which is not the native display type for our Windows and Mac. So we have to use an X server, which will communicate with the X client on a remote machine. So if you have Windows, you need an Xorg or a derived project. On OS X, you need Xquartz, which was included in version 10.5 through 10.7 of OS X, but in mono versions, you have to download it separately. In Linux, it's native, so you don't need to get anything special. So if you're connecting to SSH with an X connection on Windows, so far in this class we've gone over SigWinX and MogaX term. So SigWinX is supposed to be easily integrated with an X terminal that it comes with, which you can get it set up quickly, which I have not been able to get it to work with the one that it came with. But you should be able to just start your X11 server and the terminal, enter export display equals :0.0. For SigWinX, it assumes that you're displaying on the local host, so you don't have to put the word localhost between the equals and the colon, unless you're using a different server program. And then use ssh .x followed by your username and hostname. So if -x doesn't work, you use -y. -y is a trusted X connection, so you should only use it to connect to servers that have strong security on their own. So for the HPCs, it's fine to use -y. For MogaX term, it's fully integrated X server and terminal, so you have to set up nothing, just install it, run it, and you don't have to type -x or -y. You just connect to the server and it's running automatically. If you're using Putty, because I like Putty, you have to, before you start your connection, go on the sidebar to connection, SSH, X11, check X11 porting, and then if you're using Xming, enter the display location as localhost :0.0, and then enter your connection information. It will connect you with the next connection. If you have Xports, which is for Mac OS or OS X, which I've only tried this once and it didn't work due to some missing libraries on this person's computer. But run Xports, you have to download, and then you need to navigate on your computer before you connect to the HPC to your etc/ssh folder and modify the file sshd_config, which will be, by default, it should be control. You have to be the root user to use it, so you have to have sudo and then enter your password before you can edit the file and change the commented, or scroll down, look for the commented X11 forwarding no, and change it to X11 forwarding yes without the comment, save and exit, and then enter like you would in SigWin with ssh-y. If you're missing the libraries, I don't know how to fix them. So with the Mac, you can figure it out. And if you're lucky and these work for you, connect with X11 connection, and to launch Gaussian remotely, you can just type gv and that'll open an empty Gaussian window. If you want a specific file, navigate to the files directory, use Gaussian followed by the file, and then you can open that.
Okay, well, thank Russell. Do not leave. We will have questions for you, for sure.
Sure.
You focus camera on you. No, stay in the camera so that you see it. So, yep, please.
So earlier in your presentation, you said that in order to run qsub in your PBS script, that
Yeah.
the PBS script needs to be in the directory you're working in.
Yeah.
I commonly don't do that. I put it in my bin for jobs that I run
Oh.
continuously. So. I don't
And
think
then
that's
do you
strictly-
have to add a path, or will it? You just type qsub and it knows it.
Yeah, you just. Well, yeah, if it's in your path, in your bin, it's fine. And as long as you have that command like cd to o workdir in your PBS script, it works just fine.
Do you edit the? How do you edit your name? Do you add another script to pull a name out of your input file?
A lot of times these files that I'm running from there are the same and they run really quickly, so I don't care.
Okay.
Yep, please.
Russell, once you have a SeeCast account,
Yeah.
would you open GaussView in like the same manner as like the USD route?
Gaussian is not installed on SeeCast, so you can't use it.
So what would be the point of like typing in the Gaussian and filling out the user agreement for SeeCast? I mean, like not SeeCast, but
Oh, so Gaussian is installed on SeeCast. Gaussian is not.
Oh.
But if you're using like JMOL to view your files, you can use the JMOL command with your X connection to view things on the SeeCast.
Okay, cool, thanks.
Austin stole my question. But I want to ask it once again, maybe in different form. We all got understanding of it, but maybe your verbalization will help all of us to make it stone hard. At the beginning of your talk, you did instructed us that one needs two files, job assignment for Gaussian and PBS script, which both are text files, to run successful Gaussian job. Why do we need X forwarding connection to a supercomputer? What to one or another supercomputer? What are possible benefits?
Well, if you want to work with something that you need a visual interface for, then you have to use X connection. If you're only doing things through command line, then you don't need it.
More questions to Russell? Please.
Your use of Putty, that's just on Windows, correct? It can't be
Yeah, I don't think that
Isn't
it's
done there.
for, but you wouldn't need it if you're on a OS X. It's a built-in tree.
So you're kind of just stuck with exports.
Yeah, I think that's the only one for the current versions. If you had an older version of OS X, like pre-10.5, there are some other alternatives.
I had 10.6.
More questions? If not, let's thank Russell once again. And the next presentation is by Christian Lewis, who will start a new chapter. We are done with technical issues of X forwarding, and now we are going to actual chemistry and building chemical models. And to inform you, we are 11 minutes late.
Well, don't worry. I will go over real quick. So, thank you for the intro, Dimitri. I will be discussing how we're going to use Gauss view, for building of the atoms and optimizing molecules in general. So to start, as we have discussed multiple times now, how to run Gauss view. Once you get connected through the server, you will then just type in a GV with the ampersand, and then you'll it will pop up, and you'll be able to start running everything. We already discussed this multiple times. So, to start, this is what, if you get into the Gauss view, then you go into the builder section, you will be able to pull this menu up, and this is what you're going to be using for a lot of your building. So to start, we have a periodic table where you can go through and select a certain atom and be able to just click on somewhere on the screen and it will pop up with that atom. There's also different selections, but I'll show you that once we get further. We have pre-made molecules that have been proven, as we discussed last night. These will be able, like benzene, pyridine, and so on. You'll be able to click on those, click on the menu, and it will pop up as you see. Then we also have functional groups. So we can put an oxide or some other type of functional group onto it. There we go. Then if you do use the periodic table where you want to connect those atoms together without selecting a pre-made or a functional group, then you select onto this button right here, and then you'll be able to form bonds between those two atoms by selecting each one, and then it will pop up the second menu, and you select the single bond, double bond, triple bond, and so forth. That'll be discussed later on with Landon. Also, if you want to select the whole molecule at once, we have a selection highlighter box, and you just pull that box around your molecule and it'll select all of it. You can delete bonds, same process as building them. And then we also have a clipboard, so once you highlight the molecule you want and you hit Control-C, it will be put onto the clipboard, and you can easily transfer that to Gauss view just by clicking on the clipboard and the Gauss view. So I'm just going to show you the menu. This is a menu for your pre-made molecules. So here we go, benzene and then pyridine and so on and so forth. You have plenty of them to choose from. Now next is your functional group, so all of these right here. Same idea as the pre-made molecules. Also, here's the periodic table where you select different atoms. As I was talking, you can select the different fragments. So if you just want the carbon by itself, so you can select that. If you want it with certain other formats, like if you want it in a tetrahedral form with the hydrogens, that is also an area to be able to select. So as I said, you go to select the whole molecule. So here's a terpyridine, and I decided to select all of them. If you want to select them individually, you just put your mouse cursor over the atom, select on it, and it will just highlight it as is. So if you want to get this onto your the directory, it's pretty simple. You can either just go a straight file save and then just save it, and it'll be in your directory because you're connected through the directory already when you pull it up. Or you can go through job submission, and you just go through the whole process. Once you hit submit, it'll ask if you want to save it. Once you get, and then you hit save it with your file name. So I have put a couple in, and it'll end up with the .com. And then you just hit save, and then the next screen you just hit cancel, and you'd be fine. Then you can move over to your terminal, and you'll be able to then look at it by typing your file name or more in your file name as we discussed before. Or you could just hit ls, and you could just see your file right there in your directory. So I decided to mess around with my terpyridine, and I got this weird wonky thing. Now, if you wanted just a quick optimization without sending it to the terminal and to do it, there's this nice little broom button right here. And when you hit that broom, it just puts in it just cleans it up and makes the bonds a little more logical, as you can see. So this is what it looks like after you hit that button. Pretty simple. And questions?
I think Kristen, with a positive attitude. So questions are welcome. I have one.
Okay.
If you do not have the answer, we can keep it as a plan for the whole group for the future. Suppose you build a composition of donor and acceptor of functional groups. They are not chemisorp, they are probably physisorp, but you want to explore different spatial arrangements to different like from top, from bottom, from side, at different angles. How do you fix one group and move another around? Is it available in Gauss view or not? How would you do it?
I feel like that's something you would have to put through the terminal, but I'm not entirely sure. I did not mess around with that.
You didn't try it? And
No.
You didn't check if it goes well with cut and paste?
Yeah, I didn't try it.
Okay,
So-
that's fine. We can try it next time when we are in the lab.
Because I remember Nilu was discussing that with you with hydrates.
Yep. More questions about some practical aspects? If no, let's thank Christian once again. And next presenter is London Jones. He is helping us to continue the journey into the world of chemical molecules, and he is the right person to tell about chemistry and molecules.
That's right. So I'm going to be talking about the optimization of molecules through the terminal, and then manual modifications of bonds, angles, and dihedral angles. So first thing, just to say I want to modify this bond that's already there, say I need like a double bond, I can just click this button right here on the builder window, and that'll open up this menu. From here, I can either do like no bond, single bond, double bond, triple bond, all of that. I can adjust the bond length with the slider, or just by typing in the number. I suppose, let's see. So in order to do that, you just click this button, and then you click the two atoms that you want to adjust the bond between. So then to modify the angle here between these two bonds, you do a similar thing where you just click this button, click your three atoms that you're trying to adjust the angle between the bonds, and you have a similar menu where you can use the slider or just type in the angle that you want in degrees. And for the dihedral angles, you just click the button on the right side here, and for some reason that happened. I'm not sure what that's all about. So I guess for those of us that aren't chemists, the dihedral angle would be the angle between this bond and this bond. So this atom is connected to that one, and then connected to that one. So similar thing, you just need to click on the atoms that you're trying to adjust, and then you can adjust your angle however you want to do that. And so say that you have your molecule and you want to actually optimize the geometry of it. You want to go into this menu here, hit the calculate thing, that will open up this menu. So for the job type, it's kind of blocked, you want to select optimization, and then in the methods tab here, you want to make sure that we're on mechanics, or at least that's how we were doing it. Hit submit, make sure that you save your file. And then from the terminal, you just want to do run Gaussian, your file name, the S flag, and floor. If you want to check the status in the queue, you just do qstat. That will pull all of this up. And then if you do tail and then your file name .out instead of .com or whatever it was before, then that will it will give you the last little bit of the file. And what you want to see is normal termination of that file. Otherwise, you have an issue. And that's it.
Oh, let's thank London for being champion in reality and interesting talk. Any questions to the presenter? Jabet, please.
I'm just wondering, is a dihedral angle is a bond between the two angle between the two bonds?
What's that?
Is a dihedral angle means angle between the two bonds or something else?
So as far as I understand it, the dihedral angle would be the angle between this bond and this bond. So they're separated by one bond, and it's the angle between those two. So like if I were to increase the angle, it would basically mean that I'm spinning this one out that way.
I guess it's the angle between the two planes formed by this bond and the other line. It's not an angle between the two bonds.
Yes, that would be true. Yeah.
More questions to London about?
Yeah.
It's not really a question, but can you go to your second or third slide?
This one?
Yeah, just letting people know, I did this mistake and I couldn't figure it out. But it says atom 1 and atom 2 and atom 3. If you don't have one fixed, then the entire molecule is going to rotate in a really weird way. So you got to make sure that one is fixed. Atom 1 and 2.
Good to know.
Not atom 2, 1.
Yeah, thank you, Lisa. More questions to London about the dihedral angles?
I have a question. When you optimize, I guess, a structure that, well, you have a number of carbons that have too many bonds to it. How will that work out? Because well, carbon can only have 4 bonds. You have 2 carbons, 5 bonds on them.
Could you point out which ones those are, I guess?
Go back to, I think,
This is all the same molecule the whole way through.
right there, carbon number 3. Has 5 bonds on it.
Oh,
And then
yeah,
the
it does have
carbons
that one
right
there,
there, that
doesn't it? I didn't realize that. I did not take a screenshot of what this looked like after I optimized it, so I'm not sure if that'll actually get rid of it or not. Yeah, we definitely don't want, what would that be, pentavalent carbons?
Later on, you will see if the model is prepared not reasonable, it will explode. If there are no more questions, let's thank London once again. And we are continuing the journey into the land of Gauss view with help of Austin Brewer.
The right.
Okay, thanks for pulling that up too. All right. So people who are in physical chemistry forgot that today's the day you dress up because he uses this for your pictures on the rest of the presentation. So
I like the shirt more.
yeah, I know. Well, you guys failed on that. So I'm just going to go over a few Gaussian applications or Gauss view applications. They've been covered already just a little bit by both Christian and Landon. What I'm going to bring up new is pre-made radicals. As Christian was talking about, there's pre-made molecules that are actually in the Gauss view system. I didn't get to play with the system at all and see what those radicals were, but there's in the same sense that you can check if it's a radical, or you can also create a radical in the system by actually going into that same Gaussian calculation setup that Landon was talking about and actually checking if the parameters are set up for a radical in the system. And that being specifically that it has a charge of 0 and a multiplicity of 2, which in this case would be a doublet, and that just corresponds to a single or radical electron that's in the system to having an up or down spin on it. So that's what we're looking for in radicals in Gauss view. So you can double check on any molecule that you put into the Gauss view system, just making sure it has those parameters. I also talked about copying and pasting radicals into a model, and Dr. Killen was kind of alluding to this and how you can actually do that. There might be different steps to actually doing it in the kind of Word file or text setting, but as far as I could read through and up on is that you can simply select the molecules that you're actually trying to copy and paste, and just simply, I mean, pretty straightforward and trivial. There's copy and paste functions that are on the Gauss view setup. So you select the correct molecule, and that's your radical specifically that you select, copy it, and then paste it into a different file or setup. Then you should be able to add that radical into that setup and attach it via bonds, however you see fitting. If you want to make 5 bonds, go for it. And then the last thing is just saving and editing files to different formats. And this has kind of been discussed throughout all the presentations, but there's various different formats that you can set it up into. I kind of wish that this was bigger, but you can see all the file types that you can set up your Gauss view file as. So the main one we've been talking about is dotcom. That works the best when you're opening it up with another Gauss view system. But Russell also alluded to opening it up in JMOL, and I don't know which exact file you actually need for that, but there's different like .sdf, .ml2, .pdb1. So there's different files that you can mess around with that might work better in systems like Avogadro, or downloading it to different clusters or anything like that. So you can kind of mess around with what files you downloaded it to. Same thing too, kind of what we experience with MATLAB a lot as well, is that you can save different formats such as images, movies, and we've already seen Dr. Killen's movies of that kind of molecule, coming into the best alignment or best configuration. And that's just an example of a video that you can, show through Gauss view and how that actually works. But other than that, super trivial, just hit the, correct buttons. If you ever worked with Microsoft Word, should be able to get it.
Okay, but then question. Any questions? So on, I have one.
Yeah.
On your slide, I think number 3.
3.
Yeah, you have mentioned in the left center area that when you selecting the radical, the information about charge multiplicities is accompanies it. So if you, through copy pasting, if you combine 2 radicals, which are open shell, and you build a molecule that is known from your chemical intuition is closed shell, does it come to such configuration in the input file automatically, or you need to fix it?
That's a good question, and like I said, I didn't really get to mess around with it too much last night. But I would imagine that if you're taking the 2 multiplicities and putting them together, that the system should be able to account for that and realize that it would just automatically correlate to a regular bond or the radicals forming a bond.
Okay, more questions to Austin? If no, let's thank him once again. And we are done with Gauss view, but we are not done with the presentations. So the next presenter will be Raiden Wei, and he will help us, he and following speakers will help us to answer what to do if you do not have Gauss view. What to do if our friend has communicated us results of Gaussian calculations and we do not have access to the software. How to analyze results and how to visualize and go deeper into information that's provided in the geometry.
All right, so of that montage of things, I will be covering the precursor step to visualizing it in other software such as Avogadro and JMOL. So, like you said, if you're given a file format and they say a .out from a Gaussian job, all the information is there. The Cartesian coordinates are housed in there somewhere, and so you can use different software, home-written code if you like, to extract those details to implement into your favorite plotting software. So everything has a different format. So Gaussian likes coms, outs, logs, can be PDBs and outputs checks, and you can format the checks called F checks. Lamps takes in its own specific thing. Microsoft Word has its own specific thing. Protein database, and you could probably never count the number of different file formats that exist. So here I thought I'd just give you an example of each section of the .com file, because I think that's kind of important so that you can create your own, so it goes much faster, like you said in class, than creating it using the GUI that pops up for Gauss view. If you're able to just kind of memorize what each section, there's only 4 sections, so it's not that complicated, but you can just kind of use this as a reference. And note that hard breaks, meaning like hitting enters, is very important between some sections. So for instance, between the 0 and 1 and the starting of your geometries, there must not be a space there. So to make that clear, I made that mistake a long time when I was learning. So now, how do you make that? This was covered, so I'll probably gloss over this really quickly. In Gauss view, you can just do that. Save it as a .com, which is standard. So now, how do you convert between file formats if given a different file format or given an output of a Gaussian run? So you can use this software called Babel, which is installed both on the USD and SeeCast. And in SeeCast, you have to actually load it as a module as a precursor to its use. So you just type this at the command line. So how do you use it? So you type Babel, then the input format, say -I for the flag, say the input is a txyz file. Then you need the input, and the input doesn't actually need to have the same ending as the input specified, as long as the configuration within the file is actually in that specified ending structure. And then you can output it in an XYZ, and again, the ending doesn't have to match because it will output it in whatever format you want with whatever name you want. And then just another example, and here's some sources. I wasn't going to list a lot of different file formats because there's a lot, but these ones have probably 100 different ones. And something that I actually like to use is called newsmat. It's a Gaussian module specifically. So you have to load Gaussian first on SeeCast, but it's readily usable on the USD cluster. And I like it for doing quick from the output files from Gaussian. You can get an output file and a check file that come simultaneously from a run. So you import the check file and you output XYZ. You just get a straight XYZ coordinates from the optimized geometry, which I like newsmat for that. I have it in a script that does it really quickly. And again, you can kind of read up on it. There's not as many options for different things because it's a Gaussian thing specifically, but I like it. Yeah, so that's in general options you have to convert files.
Okay, that's fine. Questions to the speaker? Yeah, Javid.
Do you know what is the indication of end of the input file in Gaussian?
Sorry?
You know, what is the, how can you say that Gaussian your input file is now end?
Well, there's a hard break at the end after the geometry.
That's one hard break?
Well, I usually put a lot.
Yeah, minimum 3 hard breaks.
Yeah, just to be safe, I usually put like 5 or 10, because again, hard breaks are important and they signify kind of when sections end. So yeah, just be careful, and if you run into an error, just look at that first.
Any other, my question, any other functional abilities of Babel?
Yes, there's actually many different functional abilities. You can combine multiple files, you can separate, or multiple files containing different molecules, or you can do the opposite. You can have one file with a bunch of different molecules separated in space by some cutoff distance, and we'll try to separate them based on that molecule depiction. I had a hard time figuring that out last night, so I did not include that. And it has other features too. You can translate things, I think. So you can read up on that too. That's a little more advanced stuff.
Very interesting. So, in which circumstances you need to combine few molecules into one, or separate one atomistic model onto several molecules?
Well, you could be, running dynamics would give you a bunch of output files, maybe in the same XYZ separated by maybe a hard break again. So it would maybe separate them based on that, possibly. Or if you're running a simulation with multiple files and you want to analyze each one for its geometric properties, maybe you want to separate it and run separate scripts on each file.
So if you do molecular dynamics or whatever process where number of molecules is changing, how do you call it on chemical language?
Well, not fixed number of atoms, so it's got some
No, it's too physical. When bonds are breaking or forming?
reaction.
Yes. Excellent. Let's thank Braden once again. And Daniel Ramirez is invited to the stage. So he will continue a section on what to do when you do not have access to Gaussian, voluntarily or involuntarily. Gauss, you.
So quickly, I'll talk to you about alternative software for Gaussian. Avogadro's replacement of Gauss View.
Gauss, not Gaussian.
Yeah, so Gauss View, apologize, on visualizing in JMOL. Well, reason why we would want to try to find a replacement for Gauss View is it's kind of pricey, and we go to school, so we don't really got that kind of money to be dropping on programs like that. So there are a number of freeware programs out there, and a couple of other premiumware programs that are not as expensive as it and does AB initial calculations as Gaussian does. But I'll briefly mention them. So JMOL is one of them. We pretty much by now we're all familiar. We've worked on it in lab a couple weeks by now, and give or take, this is sort of what the interface of JMOL looks like, and seems like benzene's a very popular molecule in this course. Decided to show what a benzene molecule would look like in a JMOL program. Another program that was mentioned, but we haven't. Wait, yeah, we did play around with it last week in lab, but it was Avogadro. That little panel right there is blocked the name, but also once again our benzene molecule sort of has the same type of interface as JMOL does, and definition, same thing, used for research, visualizing purposes to understand what it would look like. Other alternatives to these two other programs is Spartan, which is a premiumware. Gamis is a freeware program, open source code. It was actually developed by a research group in Iowa University. Does AB initial calculations, and you can play around with the code and edit it to your liking. If you don't like how they coded a certain part, you could mess around with it to your liking. QChem and Jaguar are both also premiumware programs that also does modeling, but that's more along the lines of whether you want to pay for those programs or if your university has Gauss View for your use. And let's talk about how to build, optimize, and save something on Avogadro. Building a molecule with Avogadro is simple as this. There's a little panel right there that we use. Go up to a little thing that's called a pencil. The software calls it a drawing tool. And then we just randomly spam atoms on it to make a bond between them. You just click and drop, connects it. When you click on the drawing tool, here's the elements over there. It's not going to be like a nice little periodic table. It'll be a little drop-down bar. You could also change your double bonds and triple bonds right there. And once again, this is our benzene molecule, a really ugly one, but it's okay. The program will take care of it in a second. How to optimize something? Go to something that looks like an E, or the program likes to call it an auto-optimization tool. When you click on that, here we have a little toolbar that pops up. Just simply hit start, and then it'll try to figure out a pretty good optimized structure for whatever you drew before the software can determine what you drew. And also, there's a quicker way of building something if you don't have the patience to draw something. Say we could go right here to just open a file, go to import, fetch it by chemical name, fetch from the URL, fetch from PDB. Or if you already have a molecule file, you could just load it into it. And doing this way will save you some time. And if you're on a laptop without a mouse, if you don't want to play around with the trackpad too much, just type in the chemical name and it'll draw it for you. And saving it, simple as hitting the file save as any other program that was written like in the last 40 years. And there you got a huge amount of types of file programs, extensions that you want to save it in. There's a gamma input I was talking about earlier. Common molecule names, Gaussian is up there too. PDB, mole, XYZ coordinates if you rather want it in that format. Many types of formats you can save it in. JMOL, teach you how to load, measure, and play movies. Not too much on how to play movies because I was playing around how to do it, but I'll talk to that in a second when I get to it. So pretty much loading a molecule, same way, file, and these are the two options I learned how to do it in the time I was given. So if you hit the PDB option, same thing as before, just type in the chemical formula, it'll bring it up to you. Or if you know the name, you'd rather type in the name, go ahead and type in the name, it's the same thing. And it'll bring it up to you. So measuring distances, simple as just hitting the ruler. Just like I guess real old application, we use ruler to measure something. When you do that, I'm not sure if you can see it on your papers, the distances, but whenever you do hit the measurements, there's a little table right there and tells you exactly the nanometer length between which two atoms you selected. It also tells you whichever you hit A and B, tell you if it's a carbon or it's a hydrogen in case you don't know what atom you're exactly trying to look at. And that's simple as that for measuring distances. And for animation, just go to Tools, Animate. You could even check out the vibrations if you like. Also got transfer spectra. So you just hit all these right here, and then JMOL also has a little thing that's called a script. You could write your own script in it. So you could say there's a certain amount of atoms that's hiding behind the initial geometry that you have it. Set it to a loop between 180 degrees back and forth, so you can show basically everybody what it looks like all around it. So you can hit a 360 thing. You can hit codes for doing X rotation, Y rotation, Z rotation specifically, even the translational rotations. If you like, it's just you can program it to your liking if you want. And I'll open up the floor for any questions.
Okay, let's thank Daniel. Any questions about software he introduced you wanted to ask him? Jabat was first, but
I have just not actual question. I'm just a little bit confused about the other alternatives. You listed some software there. Is those similar to Gaussian?
Similar to Gaussian, well, some I guess were more of a alternative to Gaussian, because say like Spartan, QChem, and Jaguar, they're pretty much like AB initial calculation programs. If you don't have them, I think Gaussian is like what, a $9,000 program. Those programs are offered.
Gaussian is like 80 Gaussian is not that.
Yeah, I guess in that case, yeah, Gaussian is sort of different. I guess in that state, it's just what, modeling program.
Bryn, you developed a question.
Your bed stole it.
Russell?
So, say you have a really information-rich output file, like so you did like a relaxed scan of a potential energy surface, where you have both lots of coordinates and also a lot of energy values for each set of structures you made. Are there any softwares other than Gaussian that can display the coordinates alongside the energy values for each of the structures that you have?
Well, I'm pretty sure you just like, well, say like, well, Avogadro, and you know, you had all the basically types of formats you can save the file to. You can just pretty much open it up like you would in any other program. Whatever type of file extension, whatever type of programs you like to use to look at that information, you just save it as that format.
For either JMOL, Avogadro, or Gaussian, did you mess around with it all and see if there's like a limit to like how many molecules you can put into like a file? Out of curiosity.
No, I was just trying to I was trying to write my own script on how to animate something, but I ran out of time for that, so I didn't get to play with that feature.
Anyone wants to comment on this?
I don't know. I was just reading stuff like last night, and they said that Gaussian will sometimes like crash if you get.
How many?
I think they said like over 500.
That's quite a bit. Yeah.
No, 500 is not too much. If you do nanoclusters, quantum dots,
Right.
the number of atoms ramp up very quickly as you increase diameter. It's like cube of diameter.
So it'd be maybe interesting to see between the programs which one can actually handle the most.
JMO will not crash at 500 for sure. More questions? Which files do you need to have in your hand to do animation?
So you just take the JMO program and then you just save it as a .mlv.
No. Which input file you need to feed into JMO
Just the coordinates. I didn't get to that far. I was working on that whenever you.
So you need to have coordinates at different reaction stage or different time step.
Yeah.
It's not one coordinate file.
No.
Okay. If there are no more questions, we'll thank Danny once again. And there is a last but not least presentation by Vijay Shah, who is his presentation is of very high importance for those of us who are interested in practical research. When we will be doing research projects, we will need models that we want to model, and some of the models that are interesting for community, for the world of chemistry and materials studies, are rather big models that a human can be tired to draw. So Vijay will tell us where to take models if you do not like drawing.
All right, thank you for the introduction. So first off, I'm going to talk a little bit about SIF files. They stand for crystallographic information files. And basically what they do is they store energy about the different crystal structures that you have or different volumetric properties of your system. So they can basically give information about the electron densities of your system. And usually one does not actually write these files by hand. They actually are generated through software when you're doing X-ray diffraction experiments. And kind of like a fun fact about them is that you can only have 80 characters per line. So that's something that's listed on the International Union of Crystallography's website. They have like an entire page for like file syntax. They have a very long documentation manual as well. And most of the SIF files come from the crystallography open database. So whenever there are publications that use SIF files, they're posted on this website. And this allows other people to go and use different softwares such as Vesta, which I'll be talking about starting on the next slide. They can actually visualize the different structures that are used for the publications. And you can also convert SIF files to other file types. Vesta can actually do this as well, so I'll elaborate a little bit more on that on the next slide. So Vesta stands for Visualization for Electronic and Structural Analysis. The extra T in the name comes from the first T in structural, excuse me. I'm not quite sure why they did that, but Vesta is a free software that you can download on the internet from the website at the bottom of the slide. And basically what you can do with it, you can create different crystal structures, you can import data from many different file types, and if your file type is of a certain type, for example a SIF file, then you can actually view electron densities, nuclear densities, and other properties of the system just by going to the utilities menu after you import the data. And then there's some important stuff about boundaries and labels. I'll talk a little bit about that later on in my presentation. And you can also export the data. So if you open a SIF file, for example, or you create your own crystal structure, then you can actually export it as in the form of coordinate files, PDBs, or even SIF files. So first off, here's just a simple example of a body-centered cubic structure. So what you can do is you can just go to, you can open Vesta and create a new structure by specifying the different basis vectors for your crystal structure. So this allows you to use many different types of atoms, and you can specify the type of lattice that you want your crystal to be. And here's just an example of a visualization of a SIF file. So this is one that was on the crystallography open database, and basically, as you can see, there's like a unit cell, and then there's a bunch of different atoms that make up this structure. So you can actually use boundaries in order to get a better visualization of the system itself. So if you just use the left-hand side of the screen where it says boundary, then you can actually change the minimum and maximum dimensions of your system. For example, the one shown, or the dimensions of the system shown in the actual figure have minimum coordinates of 0 and maximum coordinates of 1. But if we were to change all of those maximum coordinates to 0.25, then it actually just reduces down to this little part of the structure. So you can increase that as well. And I tried increasing that to 2, 3. You can go on and on. As you increase your maximum coordinates or as you decrease your minimum coordinates, the number of atoms is going to increase, and that's actually going to slow down your program. But overall, the website for Vesta states that I can handle nearly unlimited amount of atoms in there, although it will slow down a lot. And another cool feature is that you can actually label your different atoms as well. So that's just done on the objects pan, and you just basically check to label every atom in your system. And yeah, with that, that's the end of my PowerPoint. So thank you, and I'll be happy to answer any questions.
Okay, well, thank you, Zach. Any questions on this subject of presentation?
Yeah.
So you were talking about selecting atoms and like giving them like letters with numbers to determine which one is which. You said you could select them all. Could you select as like a certain type, say like just carbons or like just like metals?
Yep, that's a good question. Yeah, so you can actually go through and select different types individually. That's actually what I did in order to get all of the labels on here. So you can see there's like, actually I don't know if it's like clear back there, but there's like different types of atoms here, so like capital F for fluorine, and then there's just different numbers next to the letter F, so that just specifies atom or fluorine atom 24. So you can go in and just choose individual atoms, or you can choose an entire group of atoms.
Okay.
So I mean, you didn't really cover this, so you may not have the answer. But I've messed around with it before, and if I don't want to like make my own lattice with my own basis vectors, they have like a preset. You know, you can go in and choose a different lattice, and they have these things called spatial groups. Do you know anything about that? Like what to choose, because there's like 100 of those things, and you don't know what any one of them means.
Right. Yeah. There's. Yeah. That's also a good point. Yeah. When you start up and you're trying to create your crystal structure, they give you tons of different choices. And as to how to determine which one to use, I'm actually not sure about that. Yeah, I got an introduction to this software in one of my previous courses, and we just worked with the very basic cubic structures. So aside from that, I'm actually not 100% sure as to how to determine which one to use.
Satisfied?
Oh yeah.
More questions? So our goal is to save the effort. If you want to go through crystallography database and simulate in Gaussian only this metal-organic complex rather than the whole periodic structure, do you see any problems to extract and save this molecule out of your bigger periodic thing?
Yeah. So
how would you do, and are there any difficulties?
Yeah, so I guess one of the difficulties would be determining exactly what you should have for your boundaries. Because if we go a couple of slides back, you can see that there's many different different structures of the same type. And as you were to increase your boundaries, you get more and more of these structures just repeating over and over. So one of the difficulties would be kind of just playing around with the boundary points in order to get the correct, I guess, amount of atoms you're looking for, the correct structure that you're looking for. And I believe that once you do that, you would be able to export just that portion of it into a file. I'm not 100% sure about that, though.
Okay. I have more
Yeah.
to ask. So it will be civil and provocative question. Why CIF files and COD database doesn't contain information for standalone molecules? Try your best.
Yeah, I'm guessing because they're just easy to create, or they expect people to use other different softwares for that.
No. It is. This question is not to programming and software. It is scientific, physical question.
Okay.
Why open crystallography database doesn't have standalone chemical molecule like fullerene or whatever you want, metal organic complex like ruthenium-3 bipyridine, but it has everything stacked in the form of this masked periodic cells. And if anyone from audience wants to help, just give sign, raise hands. Okay, so please.
Yeah, whoever wants to answer.
You probably have the correct answer. So my guess would be though is that if you're like trying to simulate a lattice structure, you can't have a lattice with a single molecule.
Complementary opinion.
These structures are obtained through powder diffraction and stuff, so they're only obtained in its lattice structure. So that's how the information is saved, so you can compare it to your own experience.
So a single crystal. Well, not powder. So is it clear for everyone? Anyone else in the audience wants to add? So this is kind of point to advertise course by Angel Ugrinov, who is rare expert in the world, and he is hired at the department, and he does the whole course about this thing. So the principle of X-ray diffractometer works only for periodic structures. There is a diffraction pattern of X-ray beam that scatters from all repeated molecules in a periodic lattice. If they're not repeated, there will be no signal. Therefore, this nice tool will work only for such molecules or structures that are possible to crystallize. Of course, it will work for any bulk, and it will work for structures that form super lattice of like one molecule, another set up at the same distances periodically. Well, thank you for inspiring the discussion and for your nice presentation. Let's thank Vijay. So many thanks for all attendees who presented and participated in the discussion. So with this, I'm closing two things. I'm declaring closure of today's session of presentations and closure of first chapter in computational chemistry course. From now on, you are entitled as certified experts in molecular building. And when we meet next week, we'll start exploration of electronic structure. Please join me thanking each other.
I'm a wiener.